quizzes. Most of you did really, really good. I think all of you did really, really good on this quiz. Let's just go through the answers real quick. So the first question had a scatter plot and it looked like it was going down. And who did I get to write this one up? Shannon, do you kind of want to explain why the correlation was negative?
Well, if you look at the graph, it's just look like they're going down the lines.
Perfect. Nice job. And then I got Emily to say which one of these numbers would be the correlation coefficient. Why did you choose negative 0.7?
It's less than 1.
Mhm.
Also the negative signs, but negative.
Yeah, perfect, right? Negative correlation coefficient. Any questions on number one? Sounds good. If we flip over to the back, we dealt with like the actual equation with the linear relationships and things like that. Let's take a look at part A. So this one was telling us, okay, if the driver has 10 years of experience, what's the amount paid? Was that Maya who wrote that one up? Do you kind of want to take us through your steps here? Mhm. Perfect job. Any questions on part A? All right, if we scroll over to part B now. Oh, here we go. Part B was like, okay, what if the driver has a $90 car insurance and I want to know how much experience they had. Who wrote this one up? Alex, do you want to take us through your steps here?
Okay, so since we know the dollar amount, that would go where Y is, because X is the years of experience. So it would just be 90 equal 97 minus 1.45x, and then isolating X with subtract the 97 to get negative 7, and then divide the negative 1.45 to get 1.
Perfect job. Any questions on part B? All right, very nice job on this one. I think everyone pretty much had a perfect score, if not close to perfect. So what we're gonna do now is switch to new stuff. Okay. So I wish I got myself a little bit more prepared before class, but hopefully this won't take too long. We have a whole new set of guided notes, so no need to take anything out. Thank you for reminding me of that. I completely forgot about that, but yes, let's do that. I literally told, oh my gosh. I literally told myself that we were gonna do that today, and I completely did not think about that right now. Okay, quickly go over the last question. I think we did a lot of practice with solving systems of equations. Let's just do the last question so we're kind of all caught up and we have a little review of how to solve these. All right, so checking out my notes. We talked about solving systems of equations and we had a lot of different techniques to do that. One of the techniques was elimination, where we could multiply everything or in one equation by a number. We're gonna get two of the equations to match sign or match numbers, but have different signs, right? Once we have that done, we can add together the equations and solve for one variable. Once we have one variable, we plug it into one of the equations to get the second variable. Okay, so we did a couple of those. Let's do the very last question. Okay, so I know this is kind of reaching back to last Wednesday, but we did talk about, okay, what if we have a word problem and we have to come up with the equations on our own, okay? Now, I don't think it's too hard to figure this one out, but we have, let's see, the cost of 5 squash and 2 zucchini is $1.32. And then you also know that 3 squash and 1 zucchini is 75 cents. Okay, we want to find the cost of each vegetable. Now, I've got to say, these prices are pretty low for these days, but I guess this question was written a long time ago, wasn't it? Okay, let's go through this. We have to have 2 equations, but before we come up with our equations, we definitely have to have some variables going on, right? Now, if you want to use X and Y, it's fine, but I like to make my variables go with what they mean, okay? So we have squash and we have zucchini. Okay, what variable do you think goes with squash? Yeah, I think I heard it, S, right? Sounds good, okay? And what about zucchini? Z, right? And to make them look different, I'm gonna put a little line through my Z so you can tell the difference between an S and a Z. Okay. Now that we have our variables, I have 5 squash, 2 zucchini being $1.32. How can we write that as an equation? Harris? Perfect. Okay, so 5 squash and 2 zucchini equals $1.32. What about this second equation? Harris? Perfect. Okay. Now we have our 2 equations. I've even stacked them on top of each other so you know that the S's go together, the Z's go together. Since the bottom equation has like smaller numbers, maybe that's what I should multiply to get the 2 variables to match. What do you suggest me multiply the bottom equation by? -2, right? Because let's see what happens if I do that. I'm going to multiply everything by -2. Okay, and that gives me, well, the same equation on the top. And on the bottom, I've got -6s minus 2z equals 0.75. Once we are here, looks, oh, thank you so much. I am not on my, no, I am not on the top of my game today. I'm sorry about that. 0.75 times -2 is what, -1.5? Okay, good. Okay, I'm gonna say I did that on purpose, but I didn't. All right, now we have our z's matching numbers, but they are opposite signs, right? So if we add these together, we have 5s minus 6s. What does that give me? -s, good. The 2 z's cancel out, right? And what's 1.32 minus 1.5? Negative, I got 0.18. You might want to check that in your calculator, but I think we're all on the same page here. Okay. Oh, and I forgot my s. -5s. No. Oh gosh, I was like, I am not. There we go. I am not on my top of my game today. I'm sorry, guys. Okay, I'm gonna blame it on the rain. How do I get s by itself? Divide by -1, good. And I get s equals 0.18. So it looks like our squash is 18 cents, which is the cheapest squash I've ever seen, but that's where we're at. Am I done yet? No, I gotta find zucchini, right? So I'm gonna choose one of my 2 equations. Which one do you want to choose? Top or bottom? Bottom, yeah, it doesn't matter, but let's do the bottom one. So I'm gonna rewrite my equation, 3s plus 1z equals 0.75. I'm going to plug in s into my equation. So 3 times 0.18 plus, well, 1z, just z, equals 0.75. Let's see, what's 3 times 0.18? Is it 0.54? Maybe I did something. No, that's right. Is it 0.54?
That's why I got a point.
Good. I'm very bad at mental math, so. All right. And how do I get z by itself? Awesome. Subtract 0.54. And we're left with z equals 0.21? That's about right. All right. So we know what our squash costs. We know what our zucchini costs. And we're done the question. Any questions on example 6? How do we feel about systems of equations? Do we feel all right? Okay, I feel pretty confident on how much we are good with these. All right, I guess we're gonna switch gears now into something a little bit more related to statistics. So going back to histograms, things like that, we're gonna talk about these things called distributions. And to be able to talk about these things called distributions, I wanna kind of lead into how they even come about, okay? So I have this histogram, and remember a histogram measures quantitative data that can be expressed in numbers, right? So all the numbers down here are like values, and the height represents how many times things happen, right? Okay, so this histogram says how many words of each length are in a Dr. Seuss book. So it seems like there's a lot of 4-letter words, a lot of 3-letter words, but nothing else, right? Okay. Could you, I don't know, I have some questions for you guys. Looking at this histogram, what sort of trends do you see in this graph? What do you notice about it? Maybe about the overall shape. Is it symmetric, or do you think there's more on one side, more on the other side? Yeah, it looks, I agree with that. I think it's a little bit symmetrical. And I'm gonna put ish because if I look at it even closer, it sort of looks like there's a bit more to the left than there is to the right. Maybe not that much, but still a little bit more. So more data on the left side, right? And if I look at the right, it almost looks like there's a tail to the right. Like it looks like it really decreases kind of fast as we go from the left to right. Okay. All right. Now that I can look at this histogram, let's just say I'm interested in the overall shape and I don't really feel like drawing the actual bars. If I were to draw a picture of this graph, I could literally just trace a line over it, right? So essentially what I could do is I could pretend I'm drawing a little line over this graph, right? And well, that shape would be boop, boop, something like that, right? Okay, what I just drew is called a distribution. Okay, all distribution means is it's a histogram that doesn't have enough data, like that doesn't have enough detail to it, and it just represents the overall shape of something. In order to make a distribution, I don't really need to collect a bunch of data and actually draw the histogram. I can kind of just predict what the graph looks like without actually having to do anything. Okay, so distributions basically just show trends. So maybe if it's symmetrical, it'll show that. Or if there's more data on the left-hand side, it might reflect that a little bit. If there's more data on the right-hand side, it might reflect that as well. Okay. Let's talk about different types of distributions, and we'll see more of this as the class goes on. But for now, let's just look at these 3 different shapes. Okay. First shape, if you look at this histogram on the left, okay, it does look a little symmetrical, but can we kind of see that there's more data to the left than to the right? Right, so this is more data on the left-hand side. And on the right-hand side of the graph, it's not as high, right? It looks like it kind of has a tail to the right, okay? Whenever we have a graph that looks like this, we're gonna call it skewed to the right or right skewed. Okay, so that sort of language is how I say something that has a little tail to the right, okay? On the other hand, if the tail is to the left, so most of the information is on the right-hand side, we're gonna call it skewed to the left, left skewed, okay? Now, if something has pretty much equal things on the left and the right, we're going to call that symmetric because if you draw a line down the center, the left and right hand looks about the same. Okay. Any questions so far? Sounds good. All right, we're gonna take a look at these two histograms. Oops. Let's just kind of talk about these. If I were to draw the distributions, you would like draw something that looks like this, right? Okay, and both of these are about the same shape. They just have different like amounts of data in it, right? If you kind of look at this as I'm looking at it, you'll notice that most of the data points are in the center, right? So it looks like the tallest thing is about the center of the graph, okay? They also seem pretty symmetrical, right? So if you drew a line down the middle, the left and right would look about the same, okay? And these graphs are examples of a distribution that looks like this, okay? Does anyone know what this distribution is called? There's a couple names for it.
I mean, it's just my guess because we have right and left.
That's kind of smart. I like that. But it actually has like a more formal name to it. Starts with an N. Another name starts with a B. What does it look like? Looks like a bell. Good. So this is actually called the bell curve. Yeah. Anyone else know another name for it? Just the N. It's actually called the normal curve. Okay, so it's called the bell curve because it looks like a bell. It's called the normal curve because this is what is normally used. If you take anything that has some sort of relationship to each other, like, or sorry, if you take anything that's more like commonly used that has a lot of things that affect it, like the weather, like lots of things affect the weather, the temperature outside, people's ages, things like that. Everything that has a lot of factors going into it usually follow this curve. So if you took a bunch of temperature values and plotted them, it would somewhat look like this. Okay, so it's very important. It's used a lot, which is probably why it's in your psychology class. But the normal curve is very often used, and it's why we're going to focus on this curve for pretty much the next 2 days. Okay, very common, called the bell curve, the normal curve. And one thing about this curve that's really special is since it's so symmetrical, the middle point is the mean and the median and the mode. So the mean, median, and mode are right in that center of the graph. It's right there in the middle. Okay. Now, before we talk about anything too crazy, there's two symbols that I'm going to be using a lot, just so I don't have to write this down a lot. First, we're going to talk about the mean. And the symbol I'm going to use for the mean is this symbol right here. It looks like a U with a little tail. Anyone know what this symbol is called? It's the Greek letter for mu. So it's basically the Greek equivalent of M, but mu is what we call this, okay? And when we're gonna talk about the standard deviation, which is how spread out the numbers are, right? We're gonna use this symbol, which looks like an O with a line on top. And this one's called sigma. Okay, so M and S for mean and standard deviation. Okay. All right. So what I'm going to do is I have a couple of graphs that I want to go through. They're all normal curves. And I kind of want to talk about things that might happen with these, okay? We all know that in a normal curve, we said if we drew a line down the center, the mean, median, and mode would be in the middle, right? So I know that mu, or the mean, is in the center. Everyone agree with that? Okay. Now, since I'm trying to be very abstract, like I don't have a question that's telling me what the mean is and what the standard deviation is, I'm going to just use my symbols to kind of draw other values on the x-axis, okay? And the way I'm going to do this is, I know that the standard deviation is a number, right? It could be 2 or 30 or 40 or whatever. I can take my mean and add on one standard deviation, right? So a point to the right would be the mean plus whatever number the standard deviation is. Okay. Now, I can also go the same amount further. And wouldn't that be the mean plus 2 standard deviations? Okay, if you don't see that, it's literally the mean plus a standard deviation plus another one, right? Okay, and what would the furthest to the right tick be? Perfect, mu plus 3 sigma. Okay, no, I don't have to go to the right. I can also go to the left, right? I could go 1 standard deviation to the left of the mean, but what would that point be? Yeah, right, it'd be mu subtracting off a sigma, right? Be mu minus sigma. Okay. Now, of course, the next point would be mu minus 2 sigma. And then the third point would be mu minus 3 sigma. Okay, so what I've done is I've wrote down the mean and I've gone 1 standard deviation, 2 standard deviations, 3 standard deviations to the right of the mean, and 1, 2, 3 standard deviations to the left of the mean. Okay, so that's all that means. What I'm going to do is I'm just going to take some time to write this scaling on all 3 of my graphs. So if you don't mind copying this down with me, I want to use the same scaling for all 3 of these. So what we're going to do, since the normal distribution is used a lot in psychology and temperature and pretty much any sort of thing you can take a statistic on, we're going to talk about, okay, what if I'm interested in how much of the data is within something from the mean, okay? And to make that easier to understand, we're going to start by taking a look at how much data is in between 1, 2, and 3 standard deviations of the mean, okay? So what I'm going to do, I'm going to draw 2 lines that kind of section off the middle of the top graph, okay? And I'm actually going to shade this in, okay? Okay. And this graph is just a basic histogram, but I drew a very generalized version, okay? So I'm focusing on the middle between the mean minus 1 standard deviation and the mean plus 1 standard deviation, okay? The way I'm going to say this is I'm going to say that this data is within 1 standard deviation of the mean, right? Everything that I just shaded in pink is between, well, if I go 1 standard deviation away from the mean, okay? Now, there is a way to kind of prove this mathematically. It takes a while, but this is used so often. Okay, the normal distribution is used so often that it's kind of just known that, let me just make a little eraser here. It's known that 68% of the entire data lies within 1 standard deviation of the mean. So it's kind of just generally known that 68% of all the data of everything underneath this histogram or that line is between those 2 values. Okay. All right. Let's go down to the second graph. And well, instead of thinking about 1 standard deviation away from the mean, we can draw 2 standard deviations away from the mean, right? Now, if I shade in this area is a lot bigger than the first area because I'm adding on that extra 2 standard deviations, right? And of course, we're going to call this within 2 standard deviations of the mean. So this is within 2 standard deviations from the mean. Okay, and since statisticians, pretty much anyone who deals with data works with the normal distribution so much, they kind of just know that, well, 95% of the data is between these 2 values. Okay, so between going 2 standard deviations away and going 2 standard deviations to the right, we know that 95% of everything underneath that histogram is between those 2 values. All right. Let's go, let's do 3. So it's even kind of hard to draw my lines here, okay? If I drew those lines and shaded everything here, okay? Now that's pretty much the entire graph, right? There is barely anything underneath that histogram that I haven't shaded in, okay? Let me erase this. This is of course within 3 standard deviations of the mean. It's generally known that 99.7% of the data lies between 3 standard deviations. Now, if we go further out, the difference between 99.7 and however much more the little extra that I'll tack on won't really matter. So we usually stop at 3 standard deviations. But what we just done is I've actually established this rule called the 68, 95, 99.7 rule. It's a very creatively named rule. And what this explains is that, well, in a data set, I know that between this number and this number, 68% of the data lies. Between 2 standard deviations from the mean, 95% lies. And within 3 standard deviations, 99.7 of the data lies. Okay. Now I know this was really abstract. Let's do an example and I think it'll clear things up as to what this actually means. Okay. So I have the rule kind of stated out, but let's go to an actual example. Okay. So we know that the scores on the test are normally distributed. And this is really important that it said this because this rule only applies to normal distributions. Okay, it only applies if the distribution looks like a bell curve. Okay, and let's say that the mean is 65. Okay, so the mean is mu, right? And the standard deviation is 8. So sigma is 8. Okay. So first question. Oh, by the way, before we even go to this, basically this means we have a normal distribution if you want the picture. We know that the middle or the mean is 65 and we're going 8 and we're using 8 as like our scale on the x-axis. Okay. What score is 1 standard deviation above the mean? How would I find that? Perfect, 65 plus 8, right? So we're going the mean plus 1 standard deviation. Okay. Well, that number is 73. I know that because I pre-calculated it and I can't do it in my head. Okay. And then how would I find below them? Paris or I'll do Paris. 65 minus 8, right? So 65 minus 8 is actually 57. So that's mu minus theta, or sigma, sorry. Okay, so what I've done is I've taken my mean, I've added on 8, and I've subtracted off 8. In our picture, this is taking our mean 65 and adding on 1 standard deviation 73, subtracting off 1 standard deviation getting 57. This is kind of like our first top graph, right? So going up and down 1 standard deviation, okay? So using our rule, what percent of students score between 57 and 73? 68, good. Okay, and the way that you know this is because you're going to memorize this rule. Okay. Any questions on part A? All right, let's do part B. I think we can make things a little bit faster here. What score is, how would we find what score is 2 standard deviations above the mean? 65 plus 16. The way I like to do it, because I'm very bad at doing things in my head, is I'm just gonna add on 2 standard deviations, 65 plus 8, which is 16. And that gives me 81. Okay. Now below the mean, I guess we have to subtract 8 twice. So 65 minus 8 minus 8. And that gives me 49. Okay. And if we think about the picture, we know that the mean is 65. We already went up to 73 and 57. And now we have 81, which is 2 standard deviations above, and 49, which is 2 standard deviations below. This is kind of like the second graph in our abstract picture, okay? What percent are between 49 and 81? 95, good. And you know that because you memorized this rule and you know that 95 is 2 standard deviations away from the mean. Okay, I'm gonna give you like 1 minute to work on part E and F, and then we'll go over it as a class, just so you get in the groove of doing this on your own. Are we good? I think we're good. Okay, so to find 3 standard deviations above the mean, let me just do the first one so we're on the same page. I'd add 8 3 times, right? And what number did you get for above the mean? 89. Below the mean, you'd subtract 8 off 3 times. What did we get for below the mean? 41. And what percentage is between those two numbers? 99.7. Perfect. Okay. Are we all good on this 68 or what? 68, 99, 99.7 rule? Yes. All right. Now we've talked about this rule and it is very useful because we're always interested in between 1 standard deviation away, 2 standard deviations away, 3 standard deviations away from the mean. But sometimes we don't want to be just constricted to 1, 2, and 3 standard deviations away from the mean. Sometimes we want to go like 1.2 standard deviations from the mean or 0.5 standard deviations away from the mean. And because of this, we have this thing called a z-score, okay? Now, a z-score essentially is saying how far away from the mean we are in terms of standard deviation. Okay, and I know that sounds weird, so let me just go through an example here. Now, I drew this very badly drawn normal distribution here. We know that the mean is in the middle, right? Okay. We already showed that we could go 1 standard deviation above the mean, right? Another way of saying this or showing this point here is saying z equals 1. Okay, so z-score of 1 means I'm 1 standard deviation above the mean. Okay. I can go 2 standard deviations above the mean. What do you think z would be there? 2, good. Okay. Let's go backwards. So what if I went 1 standard deviation below the mean? What would, oh, -1, good. Okay. And let me do this point here, and I'm gonna try to make my thing a little bit smaller here. What if I went, I don't know, half for above the mean? So this is mean plus 0.5 standard deviations. What would z be here? 0.5. Okay, so all the z-score means is how far we are going in terms of standard deviation above or below the mean. Okay. So for example, if the z-score was 1.5, well, we would be 1.5 standard deviations above the mean to the right. Okay. Now, there is a way to kind of derive this score. I'm not going to go through that, but I am going to show you this formula that is used to find the z-score. Okay. So of course it depends on what the mean is, and of course it depends on what the standard deviation is, okay? The z-score represents how many standard deviations we are away, and it represents an x value, right? Okay, so in order to find the z-score, we're gonna take the x value, subtract off the mean, and divide the standard deviation, okay? This is something that I want you to know, so I want you to memorize this formula. Okay, and this gives us an idea of, well, what's the mean? What's the standard deviation? Okay. I'm gonna be honest, I meant for us to do this next example tomorrow. So I'm gonna let you go. All right. I underestimated the time, but that's okay. All right. Have a good rest of your nasty day. And I will see you on Wednesday.